Poop. All right. So 5.7, we started to hit this kind of hard towards the end of the trimester. I got a 3-kilogram ball, okay? If I'd had a 10-kilogram ball or a 20-kilogram ball, what thing would have been the same regardless? Gravity would have been what, though? 30 newtons on this thing, okay? But what's the same regardless of the mass here, gravitationally speaking? Awesome. All right. So if I'm drawing a velocity versus time graph of this thing, I guess the first thing I got to think about is the free body diagram. Okay, and if this is a 3-kilogram mass, this gravitational force is 30 newtons. It's the only force acting on it. So the unbalanced force acting here is also 30 newtons. So I guess I should write it like this. Fu equals ma. So 30 newtons equals 3 kilograms times a. Okay, therefore, my acceleration is 30 newtons, not over 30 kilograms, Mr. Harding, over 3. Who's got a calculator? Awesome. Okay, 10 newtons per kilogram, that's equivalent to 10 meters per second squared. I'm doing that because then on my velocity versus time graph, that's going to be my slope. Okay, this ball is dropped. Like perhaps this class should be for some of you. So I dropped this thing, okay? What's that going to look like at the beginning of the velocity graph? It's going to start rest. It's going to start from 0. It's going to go from there. Now, if you're savvy, maybe you catch that it's moving downward and we want to graph it below the axis, but I've seen your quizzes. So we can draw it this way. This acceleration is 10 meters per second squared. That's what I figured out over here. All right? And it's going to fall for 3 seconds. So I can do a little math here. If the slope is 10, that means it's going to go 10 meters per second for every second. If I do that for 3 seconds, this is going to be 30 meters per second. So this thing goes 90 meters in the end, yeah? Don't fall for that. This is a triangle. So I've got 1/2 of 3 seconds times 30 meters per second. So that's going to end up being 45 meters for this one. Okay? So I guess what I'm saying is if you had version 1 of the quiz and you've got 45 meters for that answer, make sure that you've got a 3 for 5.7 in the power score, but you probably can't look, can you? It's broken. But anyways, hopefully you did. All right? That's what's going on there. With the next one, I already give you the graph. And this is like, can you work backwards from the graph to what the diagrams are telling you? So I got a velocity versus time graph. I start off going 6 meters per second. In the end, I'm going 3 seconds. My intent was, this is a crate that's sliding across the surface, okay? So I got this thing. It's interesting after it leaves my hand. It slides to a stop. It's 12 kilograms, okay? Sliding to a stop should imply, hopefully, some friction. And again, the 5.4 aspect of this is being able to draw this free body diagram. Here's some smoosh poosh. Here's some gravity. It's 12 kilograms, so this is 120 newtons. It's a flat surface as far as I know, so this is 120 newtons as well. And then I've got friction pointing against its motion. I don't know the amount yet, but I can figure that out over here, okay? If this goes down 6 and it goes over 3, I'm going to say 0 minus 6 meters per second over 3 seconds minus 0. That's going to shake out to be negative 2 meters per second squared. That's the acceleration here. I can get the unbalanced force then by taking the mass times the acceleration, 12 kilograms times negative 2 meters per second squared, negative 24 newtons. So when I add these arrows together, arrow up arrow left, arrow down, it should result in an FU of negative 24 newtons, which is just to say that it's pointing opposite direction of the motion. That's how I know the amount of the frictional force. And so that would be what you'd need to have to get the credit for the 5.4 and the 5.2. Similar type of idea, but going the other direction. I've got a 30 kilogram crate. It's being pulled 24 meters with a force of 100 newtons. It's a 30 kilogram crate, so FG is 300 newtons. Doesn't say anything about an incline, so I'm just going to go ahead and draw my smoosh poosh like that. 300 newtons. Doesn't say anything about the force being at an angle. So I'm just going to draw that over that way. F, tension, 100 newtons. I've got a frictional force, and that's 1/10 of this FG. 1/10 of 300 newtons is 30 newtons of friction. So now when I add these all together, I go arrow up, 300. I go arrow to the right, 100. I go arrow down, 300. And I go arrow left, 30. That's going to leave a gap here of 70 newtons. That's the FU. All right. And so now I can say 70 newtons divided by the 12 kilogram mass. That's going to give me the acceleration. So I bust out my trusty calculator. 70 divided by 12. 5.83. That's the acceleration. I need that to be able to draw my velocity versus time graph. This thing starts from rest again. So my graph's going to go like that. Looks like that. This area is 24 meters because that's how far it goes. That was up above somewhere. And my acceleration is 5.83. That's the slope of this thing. Okay? So I was happy to see this in the cases where folks were doing this problem that you're recalling, that whatever this base is t, then this side of that triangle has to be 5.83 times t, because that's how slope works. So 24 equals 1/2 of t times 5.83 t. So I can pop back over to my calculator, multiply both sides by 2, gets rid of that half. So that would make the left side 48. And I take that 48 divided by 5.83. I get 8.23. 8.23 is equal to t squared. So I'm guessing this is a square root button. Yeah, there we go. So t equals 2.87 seconds. And then I can figure out the velocity if I multiply that 2.87 seconds times my acceleration. Oh, no. So 2.87 times 5.83, 16.7 meters per second over there. Okay? And so that's how I would get the velocity and time. Oh, did I screw up? What did I do? What did I do? Over 12? What's that all about? Where did I get 12 from? You got to raise your hand louder. That was a while ago. All right. 70 over 30. 70 over 30, that's going to be more like 2 point something. 2.3? Yeah, Maggie? Oh, man. So now I got to go over here. Now I got to do 48 divided by 2.3. What a mess up. 48 divided by 2.3, 20.86. That's a difference. Ooh, and I got to take the square root of that. 4.56 seconds. There we go. .56 times 2.3 meters per second. Yeah, 10.5 meters per second. All right. All right, so that's what I'd want to see. I'd want to see the velocity, the time, and the acceleration on the velocity time graph to get the points for 5.3. I'd have got 2 if Maggie hadn't bailed me out there, but that's the 3 points. Okay. The bottom one, 5.5. What is 5.5? Look at the essential understandings there quick. What's it looking for? In a word, what does it want? Pairs. So your answer probably should have included pairs. Okay. This dog's pushing 2 boxes to the left with a force of 20 newtons. Each box experiences a friction force equal to half its gravitational force. All right. So as you're looking at this, again, system schema, 1 kg box, 2 kg box, dog, surface, earth. These are all the important objects. 1 and 2 kilogram box are touching. Dog and 2 kilogram box are touching. Surface is touching 1 kilogram. Surface is touching 2. So these are all smoosh poosh. And then it talks here about friction. So there should be friction there. Friction there. Earth is interacting gravitationally with these things. So why you should do this, it helps you have the right number of forces. Of the people that attempted this problem, I think I saw 3 examples that had the correct number of forces. If you draw a system schema, you're going to struggle to not have the correct number of arrows. All right, I've got the 1 kilogram box. I'm going to have gravity going down. I know that's 10 newtons. It's on a flat surface, so I'm probably safe to say I got 10 newtons of smoosh poosh up. I've got friction. And I know the amount of it because it's half the FG, so that's 5 newtons here. If I look at the system schema, I see 1, 2, 3, 4 lines connecting. The one that I'm missing right now is the force that box 1 feels from box 2. So that's got to be in the forward direction. So that would be F smoosh poosh 1, 2. Then I draw a free body diagram for the 2 kilogram block. Now I'm going to have 20 newtons down. And I'm going to have 20 newtons of smoosh poosh up. Again, the friction is half its FG, so I've got 10 newtons of frictional force. But if you look at the 2 kilograms here, I've got smoosh poosh, smoosh poosh, smoosh poosh, friction, and gravity. I've got 5 arrows total. I've got a force from this dog, 2 comma dog, and I know that that's 20 newtons. So the other thing that's acting here, and I don't know what it is yet, is I'm going to move this a little bit, is a frictional force, or not a frictional force, sorry, is a smoosh poosh force from the interaction with box 1. This is the force that 2 feels from 1. So these are a force pair. And I've got to use some physics shenanigans to figure out what the amount of that is, okay? So I'm going to do the system trick. And I'm going to put a system boundary around 1 and 2. And so my system is 3 kilograms. So this is 30 newtons of FG. This is going to be 15 newtons of friction. This is going to be 30 newtons of smoosh poosh. And then in the forward direction, I've got a smoosh poosh of 20 newtons from the dog. I don't have to worry about the force pair because that's inside the system right now. I know all these arrows. If I go 30 up, 20 over, 30 down, and 15 to the right, that's going to leave me with an FU of 5 newtons. Maggie, have I screwed anything up yet? Okay. That doesn't give me confidence. I've got 5 newtons of FU. If I divide that by 3 kilograms of mass, that's going to give me my acceleration here. Okay? 5/3. So 1.67 meters per second squared. Now I can go back in to the other problems and take the mass times that acceleration. And I know the FU for that front object has to be 1.67 meters per second squared. Okay? AKA, that's not the right units, 1.67 newtons. So is that this force? Is this force 1.67 newtons? Run that by your neighbor real quick. Aye. All right? It's not. I got to get an FU of 1.67. So if I go up 10, I go 5 to the right, I go down 10, I've got to go past this thing so that I get an FU of 1.67. To have 1.67 poking off the side, this bit's got to be 5, okay? So there's 5 right here, plus that 1.67. This whole thing is 6.67 newtons. Here's where the force pair thing comes into play, okay? You want to be ready for that when it comes up again, which it will, because it always does. So this force right here, it's not 1.67. Hey, thing 1 and 2. Shut up. All right. Grades are in, bro. Not until 11. All right. So 6.67 newtons here means that this force is going to be 6.67 newtons here. All right. Now if we do a force addition diagram for this thing, I'm going to go 20 up. I'm going to go 6.67 over. I'm going to go 10 over. I'm going to go down 20. And then I'm going to go over 20. And if you look at how this shakes out, if this is 6.67 and that's 10, this side of this thing has to be 16.67, okay? That means my FU here is going to be the difference between 20 and 16.67. A 3.33. So now I take that 3.33 Newton FU divided by a 2 kilogram mass, and I'm going to get 1.67 meters per second squared for the acceleration. Both objects have the same acceleration because they're part of the same system, okay? So you got to have that confirmation within your work. You got to be able to get that same acceleration value for both objects. That's your way of checking, okay? So that's what's happening there. I'm starting to lose the two people that were paying attention, so I'm going to call it good at that. And if you got questions on any of the other stuff, then we can certainly take a look at it during AFT. I don't think any of you got added to my AFT So I'm grateful for that. But yeah, if you want to come in sometime, you can. Is this going to work? And yeah, why would it? All right, so over on Canvas, I've gone in and done some of this stuff. Let's see if I publish this. Is that going to help? Boop, boop. I'll leave that up. Ooh, that looks salty. Now over on Canvas, there should be some stuff if you take a glance. The COP unit, which I don't even know what that means. But then today we're talking if charts. And what I have for you is some examples of like my velocity versus time graphs, okay? If you look at this, you can see this is 0 right here. It's really hard to see unless you got it up on your Chromebook screen, but that's 0. So whatever the green graph represents is going kind of slow in the positive direction. Whatever the red graph represents is going relatively quickly in the red or in the left direction. So if I play this video for number 15, come on, Link. We should see two things going in different directions at different speeds, okay? So yeah, that agrees. The green glider is moving slowly to the right. The little red glider is moving kind of quickly to the left. After they hit, they're moving ever so slightly to the left. And that's why you see that on the velocity versus time graph here. Final velocity is not 0. And of course, I didn't do an if chart example for that, or did I? Yeah, I did. So this says it's for 16, but it's for the one we just saw, for 15. I know that because they've got a little bit of velocity in the end. They're going negative 0.03 in the end. Initially, the green was going positive 0.1, the red was going negative 0.36. Okay? So the things that I'm looking for from you in your analysis, if I grab this and pull it over onto, hey, did that concussion course. If I take this and I pull it over onto Canvas, all right. If charts, we want to take and find the area of this thing, okay? The area is going to be 0.48 kilograms times 0.1 meters per second. This one is going to be, let me put it in red here, red. This is going to be 0.20 kilograms times negative 0.36 meters per second. Those are the dimensions of the rectangle, okay? The width of this should be 0.2 kilograms. The height of this rectangle is negative 0.36 meters per second. So I'm finding the area. I want to do that for each object here. The height of that, that's the 0.1. The width of it for this one is 0.48 kilograms. I'm going to do that for both the I and the F. Okay? And here's the masses. What I'm angling for in the end is I want you to figure out a couple of additional pieces of information. Total area initial, total area final. The other thing I want you to do is for the red, do the final red minus the initial red. If I'm doing final minus initial, that's going to find me the change in area for red. And then you're going to do the same thing for the green. Do the final green minus the initial green to get the change in area for green. Now, you might not have red and green. You're going to use whatever gliders you have. But in terms of the analysis, those are the things that we need to be able to discuss here. What's the total area on the I? What's the total area on the F? What's the change? Here's the thing that breaks my brain, right? We did this a while back in AP. Change is one of the main things I want you to calculate in here, okay? And I have a wiser friend, and they refer to it this way. They say initial plus change equals final. And they swear that their students do better with that than the way that I do it, which is to say that change equals final minus initial. I don't care how you think about it. Just think about it. Okay, be kind of cautious here, because there are a couple of things that you should be able to deduce from the data that I don't want to just have to tell you. I'd like you to do a little bit of lifting here with the analysis. All right. So I'm going to hand back this chart. I was a kind party in terms of what I put into Power Escuela, but some of you have some work to do on this. That's going on you. But let's get the analysis here to you've got it, all right? And then Spencer. Yeah. No BT, no Hayden. Houston. Max. Hey. Dude. I still come and go to work. All right, so this is what you're working on right now. If you didn't hand it in, if you got questions, need further help with the analysis, cool. I have no idea what we're doing, so if they're near you, start to like loop them in on what you're doing. Okay, what? I take 0.2 times negative 0.2. Yeah, but I don't think you have a negative area. It's pretty weird when we found out this velocity, mass times velocity. Take the mass times velocity. And then we're subtracting back. Subtracting. I'm doing no subtraction. Oh, the total area? Yeah. I will be adding a negative number to a positive number. All right, it's Power School. Yeah. Got it? Score Avion. Get after it.
I got a like stamp, man.
Yeah, you don't have a like stamp this try. You don't have a like stamp this try. What have you done for me lately? All right. Here's your groups. Oh, cool. Curran. It's exciting. It's your time to shine. Come up with a theme for us for our group names. What are we going to be themed upon?
Oh,
What was our last theme?
spices.
Spices. Toppings.
Oh, that's not me.
Toppings. Come up with a. Like, are we talking pizza toppings? All right. Pizza toppings. Pizza toppings. And hey, I want you to go ahead. Hey, move around with your groups. Okay. Get with your people. Ooh, there you go.
No, various things.
So Ayana and Priska and Jack find each other. Keaton Clark and Kachuk. Spence, Evan and Tanner. Lucas and Max. Brody and Curran. Maggie Chase and Peyton. Anastasia, Mitchell and Peyton. Brody, Josh and Lucas. Alicio, BG, and Noah. Toppings. Jack Dickens. Topping. Topping. What's on your pizza? Sausage. Keaton. What's on your pizza now that you can eat pizza? It no longer has to be ice chip pizza.
Artichokes.
Artichokes. On pizza? I'd prefer ice chips. Spencer, what's on your pizza? Pepperoni. I'm not sure that's how it's spelled. Lucas, what's on your pizza? Lucas, Holly. Sausage, artichoke, and pepperoni. Cheese would be a good call on pizza. 80, what do you got? Pineapples, because you're a savage. All right. Peyton. Peyton B, what's on your pizza? Peyton B, Peyton B, Peyton B. Somebody speak up for Peyton. What's on Peyton's pizza? That's gone. What are those little fish things called? Sardines. Olives? Well, you got to be green olives. No, not really. That'd be dumb. Black olives. All right. Chase, what's on your pizza?
Bacon.
Bacon pizza. Maybe it's a breakfast pizza. Brody, what's on your pizza? Brody L. Jalapenos? Really? On pizza? Where do you get that from? Wow. Where is it available? Wedge? Oh, okay. We're not tough enough for that. Brody E.
Taco. More specific. Dorito chips.
Dorito chips, comma stale, because that's how they do that. All right. Alicio, what's on your pizza? There we go. Way to be a sport. Anchovies. All right. There's the groups. All right. Good that we were able to get to the important stuff. So, again, here's you. You're on your if chart. If you got a new kid that wasn't with us last try, you're kind of letting them help you out with the math there a little bit. Finding the total area, marginally enough task. Okay, find the total area of the rectangles, and then find the change for the individual objects. Okay, there's a slight difference in what I want. Total area for the initial, total area for the final. But then when you're calculating change, it's for the individual gliders. So what was the change for the big green? What was the change for the big gold? Or whatever you have there. All right. Well, definitely know you did. Yeah. Ooh. I got Peyton F's and it's green and gold. You just want that? We'll just change the F to a B. That's what I used to have to do on my report cards. What's up?
You know what that's about?
What that's about. You were marked school activity
You
in
got it
period
too.
3.
And we don't know what school activity we're part of.
Oh, I can look it up. Power
Thought it was kind of
school.
odd.
It's in Anastasia's folder. So I got it.
Oh, you have it. Why
Yeah.
was it in Anastasia's folder?
I don't know.
All right. I see no such indicator.
Yeah, I don't know. Katie got the same thing.
Hey, everybody. Tanner's on vacation. Let's all think ill of him. Meet the new try. Same as the old try for BG.
You want to know the total, the first total plus the second total?
So, like for the I, you want to take the areas of those two boxes if you have to, add them together. Give me the total area on the I.
But you don't want initial total plus 5.
No. We just want to compare what you had initially to what you have in the end. All right, now ultimately this should be going on a whiteboard, and this is where we screwed up because now you're in different groups. So grab it from the back. You might have to erase, change it. Maybe two of you already put together to have that back, but grab a whiteboard from in the back there. Get your if charts on there, your total areas, your changing areas. Be quick about it. If you know you're already done with this, go grab it because somebody else grabs yours and erases it. What? No, I want you in new groups. So for your new group, you're gonna have everybody's zip chart on here. Over here, you'll have the area you track control, the change for each object. Hey, Jack's got the markers.
Oh, I was going to get this. I have no idea what we're doing, but I actually look at this. I got